In this video, we're going to talk about 7.3 Objective 3, where we find and interpret best fit lines for given data. Listed on the table below are annual data for various years. The data are weights in metric tons of lemons imported from Mexico and U.S. car crash fatality rates per 100,000 population, complete parts A through D. So this data, even though there's correlation, there's no causality. We shouldn't expect lemon imports to have anything to do with crash fatality rates. So this is a silly example to show that correlation does not equal causation. So let's clear our lists here. And let's put in 230, 265, 358, 480, and 530, and then 15.9, 15.6, 15.4, 15.1, 14.9. And let's go ahead and make our scatter plot and the line of best fit using our calculator. So stat calc number 4. Our data is in L1 and L2. Let's go ahead and vars, y vars function y1 for where we're going to store our regression equation. Let's calculate that and get our R value of negative 0.98 and R squared is 0.97. So this would be about 97%. The variation can be accounted for by the best fit line. Let's go ahead and figure out the graph here. Window, we're going to start with 200 on X and go to 600 on X. And we're going to go by, let's see, 1, 2, 3, 4, 5, 6, 8. Zoom in there just a little bit. 2, 3, 4, 5, 6. Yep, there is 8. So 200 divided by 8 is just a second. It's a scale of 25. And Y min is 13. Y max is 17. And that definitely goes by ones. Let's graph that. That looks like D. We would say that the best fit line shows a very good fit to the points in the scatter plot. That's right here. Now let's answer these questions. Back to part C. Identify any outliers on the diagram and discuss their effects on the strength of the correlation. On the best fit line, choose the correct answer. So there are no outliers. Does the best fit line appear to provide reasonably reliable predictions within the range of data given? And explain. Predictions based on the best fit line could be reliable because the value of R squared is sufficiently large. However, predictions should be made with caution because there are very few data points. So, and we also know, like I said, that this is a silly example to show that we can show correlation between lots of things where there's probably no causality. So let's go ahead now and look at number 2. And we're going to put an altitude and temperature. There should be a direct relationship here. As altitude increases, temperature should decrease. That. And let's stat calc number 4. And vars, y vars. There we go. And again, R is going to be negative 0.99, and R squared is going to be 0.99. This is going to be a very good fit to the points because those numbers are so high. This is 99%. The change in y can be explained by the change in x. Let's go ahead and graph this, starting at 0, going to 40 by increments of 5, then starting at negative 70, going to positive 70 by increments of 10. And let's see here. Looks to me like it is C. Okay. And that's a very good regression line. Identify any outliers on the diagram and discuss their effects and strengths. On the strength of the correlation and the line of best fit, choose the correct answer below. There are no outliers. Does the line of best fit appear to provide reasonably reliable predictions within the range of the given data? Yes, because R squared is very large. So predictions based on the best fit line could be reliable because the value of R squared is sufficiently large. However, predictions should be made with caution because there are few data points. And this is very good. All right, let's go on to our next problem here. Let's put in our data. Brain size 952, 1011, 1019, 1198, 1031, 1068, 1025, 1051, 1155, 1096, 85, 77, 81, 95, 98, 90, 118, 128, 107, and 110. And this is trying to see if there is a correlation between brain size and IQ score. So going to stat calc number 4. Let's go ahead and put that regression equation in y1. Let's calculate. Our R value is 0.27. Our R squared value is 0.07. And let's go ahead and take a look at this data. X is going to go from, it looks like, let's see, 1, 2, 3, 4. So 200 divided by 4 is going to be 50. So 950, let's say it starts at 900 and goes up to 1300 by 50s. And we have 2, 3, 4, 20 divided by 4 is going to be 5. So this is 70 to 140 by 5s. And that looks like D to me. And there's not really a good model here. It's based off of R squared. Only 7% of the variation can be accounted for by the best fit line. Are there any outliers? Yeah, there's actually, let's see, this one up here is an outlier, and that is this. And let's see what happens when we remove that and rerun things. So let's edit, and that's just significantly higher IQ there than everybody else. So let's delete that and rerun everything now. Stat, calc, linear regression, and then vars, y-vars, function y1. We're not going to change our window at all, but it did make the R and R squared value get bigger, though not really a whole lot better, just because there's so much error in this. And that's not because of outliers, that's just because this is the real data, that there's not a lot of correlation that's there between brain size and IQ, even though we make that expression about, oh, that's a big brain play or something like that when somebody does something good. So does the best fit line appear to provide reasonably reliable predictions within the range of the given data and explain? No, it does not. Predictions based on the best fit line could not be reliable because the value of R squared means there is little correlation just because R squared is so small. Even when we remove the outlier, R squared is still too small to have any reliable predictions. Now let's look at number 4. And listed on the table below are the systolic blood pressure measurements in millimeters of mercury obtained from the same woman, complete parts A through D. So with her right arm, first I got a reading of 103, then 100, then 95, then 80, then 83. Their left arm, 176, 170, 179, 147, and 145. Something is way off, it seems like, to have gotten such different readings when we switched arms. So that doesn't make a lot of sense. We're going to run the model with the data that we have. So stat, calc, vars, y-vars function y1 there. And we're going to get an R value of 0.90 and an R squared value of 0.82. And this is going to be 82%. Not a bad number. Let's go ahead and look at our window here. It goes from 70 to 120 by tens, and then from 130 to 190 by tens on Y. And that looks like C to me. And identify any outliers on the diagram and discuss their effects on the strength of the correlation and on the best fit line. So there's a large gap here between these 2 points and this cluster of points up here. With such a small data set, none of the points are likely outliers, but we just need to note that it's interesting to us that they're clustered together in 2 clusters like that are so far apart from one another. And does the best fit line appear to provide reasonable predictions within the range of the given data? The value of R squared is high and the points appear to be somewhat close to the best fit line. So the best fit line appears to provide somewhat reliable predictions within the range of the given data. Again, we have a small amount of data collected, so we would be careful in making predictions with such a small amount of data gathered. And again, we would probably have expected that the blood pressure in the right and the left should be about the same. And we didn't get that. So if this were, this is not just something where we're interested in seeing correlation, but if we were actually gathering this data, we would want to investigate that and say, why is the pressure so much higher in the left arm? Is there something physiologically going on in the left arm that's causing the pressure to be higher, like some kind of blockage or something like that? Or in the right arm that's causing the pressure to be lower, like some kind of bleeding issue or something like that. So we don't know that. That's not what our question is here, but just look at those types of things and see when they don't meet your expectations. There might be further investigation that you might want to do when your model doesn't come out as you hypothesized. All right, that's it for this video, and we'll come back next time and start talking about our topics for Chapter 8. We'll see you for the next video.